In this video, we're going to get an introduction to Bayesian analysis, and we're going to kind of see a preview of the content of Chapter 4. So our objective here is to get what's called the posterior distribution. Let's zoom in a little bit here. So the idea is that we take our sample data and the distribution of our sample data given theta, that's known. And then also we have some prior distribution on theta. And then we want to combine those together and get an updated distribution, essentially, based on the data. And that's called the posterior. So we want to find out what's the distribution of theta given x. Right back here we have the distribution of x given theta. And what we want is the distribution of theta given x, which again is called the posterior distribution of theta, and it is updated by our knowledge of the sample data. All right, so let's look at sort of the mechanics of how to do that. So the distribution of theta given x is the joint distribution of theta and x divided by the marginal distribution of x. And then to get the joint distribution, we just use the marginal distribution of theta times the conditional distribution of x given theta, and then together that product is the joint distribution. And if you wonder why that's true, then just equate these two and then divide by the marginal on both sides, and what you'll get is the defining formula for this distribution of x given theta. Okay, so once you understand joint distributions and marginal distributions and conditional distributions fairly well, then the mechanics of this conceptually, I guess you could say, it's not too difficult to grasp what's going on here, but the practical application thereof can sometimes get a little hairy, as we will see in the example. For the first example, we're not going to deal with a whole vector of data, like a whole big random sample. We're just going to deal with one observation. This is a sort of a dumbed down version of an example that's in our textbook. Okay, so let's say theta has some normal distribution, as we see here, with mean mu and variance sigma squared. And it's important throughout to divide between those things that we know and those things that we don't know. And in this case, mu and sigma squared are both known. And then also we're going to assume that we have an observation of our data. And since we're treating theta now as random, this is x given theta, and that follows a normal distribution with mean theta and variance 1. And here theta is obviously our unknown. So we want to determine the posterior density of theta given x equal little x. And our little x, our one observation, that is also known. All right, so let's look at the solution. So because x given theta is normal theta 1, we have this distribution here. And then since theta follows this normal distribution we have here, then the marginal density is what we see there. So now we've got to go through the steps to get to the posterior distribution. And I would encourage you at times to take pencil and paper and work some of this yourself, because I'm just going to kind of give a roadmap to the methodology, but there's nothing can replace just you spending the time to do this yourself. All right, so using 1 and 2, then we can put together the joint distribution, right? Because we take the marginal, the prior, what we've been calling the prior distribution, times the conditional distribution of x. We put those together, And what we end up with is what we see there, which I've labeled number 3. And now, in order for us to get to the posterior distribution, we've first got to determine the marginal distribution of x, right? Because here's the posterior distribution formula, the distribution of theta given x. This is what we're after. And as you see there, we need to know the marginal for x. And let me just point out here, as it says, typically this marginal is written as you see there, but our book uses little m for marginal, so we'll stick with that. And so to get the marginal distribution, we're going to have to integrate the joint density and integrate out the theta. But in order to do that, it's going to be easier for us to do a little more work on the form of h of x theta. So let's start from where we were before. And what we're going to do is we're going to take this part that's indicated in blue, and we're going to express it as a quadratic in theta. Then we're going to complete the square. And I'm not going to go through each step, detail by detail, but like I said, it's beneficial if you do it yourself with pencil and paper. So you multiply all that stuff out, as you see there, and then it looks like I did a little work with the numerator. And once you complete the square, you get this expression here. So again, you should do that for yourself. And then that gives us that the density, the joint density, is what we see here. And then let's say I defined, to make this a little simpler, to make things a bit more concise, I've defined a few constants here. And notice that all of these are known because sigma squared is known. Little x, the data is known, mu and sigma squared. And then here's another one, beta. Beta is known because all of these in this expression are known. So that gives us something that perhaps is a little more recognizable. And so that's our joint density. Now combining 4 and 5. 4 is where we just mentioned that to get the marginal, we integrate out theta. And then 5 is where we got the particular form of the joint distribution. And so you see that here. We also need to make note that what we're integrating here is similar to a normal distribution, right? We're integrating with respect to theta, and here beta is a constant, as is gamma. So what we need to do is make sure we have our distribution sheet handy, or wherever you have this information. And if you're new at this, I think it's helpful to just multiply and divide by the normalization constant. And let's see how that works. So we're going to take the 1 over 2 squared sigma times e to the rho, move that over a little bit, and then we're going to multiply and divide by the square root of 2 pi gamma. And then you notice that what I have highlighted in red there is exactly the PDF of the normal distribution with mean beta and with variance gamma. So that integral is 1, and so you're just left with this part over here on the left, which is highlighted black, I think. And so it's like magic. There's no integration, there's no brute force integration required here, right? Just take advantage of the fact that the integral of a density is 1. And eventually you can get to the point to where you can go straight from this step to this step, because this integral here is essentially just the reciprocal of the normalization constant, the constant that you put in front to get a valid PDF. So then now we go back to definitions, what these things are called, and we substitute in, just do a little, that's just algebra. And then we finally get to our marginal distribution, and lo and behold, it's recognizable as a normal distribution, which we have recorded. So now we have our marginal, and we should be able to now determine what is the posterior distribution, because remember we had the formula. It's just the joint density divided by the marginal for x. So plug all that stuff in, simplify, and we get this expression here, and notice that that is also a recognizable density. It's normal. It has a mean of beta and a variance of gamma. And then just look back at what those were defined as, and you should see that it is. Now, if you compare this to what you see in the textbook at the bottom of page 80, where n is 1, remember we only did this with one observation. We didn't actually have multiples. In the book, they did this using x bar, whereas, like I said, we just have one observation. But that comports with what is in the textbook when n is 1.